Jonas is from Stockholm, and Jonas and his co-workers from Toulouse, I think, did their work at CNRS, and this presentation is entitled Investigation of Internal Tides Excited by Multiple Ridges. Excited. Mm.
Thank you. Is there a pointer of some kind? Or I just
you can use my pen if you want. That will get you most of the way. There you go.
Good. This one? No, something else. Oh, okay, thank you. So this is actually not the whole team. It's part of the team. Part of the team that's involved in the what I will speak most about. But there's also a few more members of the team on a different part of the project, which I will mention more at the end here. So I'm Jonas Nikander, and here Said Falahat, Alexandre Passy, Lucie Bordois, Francis Auclair. So this work is about internal tides, which many of you may not even know what it is. So internal tides is a kind of internal waves. Most of the people here talk about usual surface waves, but these are about internal waves, which are possible only because of the stratification of the fluid. And internal tides are internal waves excited by the usual tidal flow. And to motivate why this is interesting, I will speak briefly about the general circulation, the overturning circulation of the ocean, because that's really where this comes from. This is now a very hot topic in the general oceanography community here. So this is a simplified picture of the world ocean here, and here is one of the poles. Here is the equator, and that's the water surface up there. And so the general overturning circulation is that at the poles, the surface water gets cooled and sinks to the bottom, and then it gradually flows over the ocean floor and returns in the mid-ocean and the equatorial region up here. And now the downward branch and the upward branch are very different in the sense that these downward flow and convection events, these occur only occasionally and in very narrow plumes, so to speak, while the upwelling branch is very widespread and very slow and cannot be observed directly. Now, if you look at this kind of circulation from one more important point here is that this upwelling water then, it goes from the cold bottom water and then to the pool of warm water near the surface in the tropics and the mid-latitudes in the ocean, and therefore it must be heated on the way up here. And this heating, molecular diffusivity is not enough for that. This heating is achieved by mixing. And this mixing is done by breaking internal waves. And if you look at this whole circulation from a thermodynamic point of view, it's actually driven by this mixing. And this mixing, these waves are excited externally by tides and by winds. So that's why this is so important for the general circulation of the ocean here. So internal tides work like this. You have some hill here on the bottom, and then because the usual tidal motion here, the whole water column oscillates back and forth with the frequency omega here and the amplitude velocity u0. And then then the water is stratified, so these lines here are density surfaces, and when they move back and forth over the hill, the density surfaces are perturbed, and this creates or excites internal waves radiating off the hill here. So to describe this theoretically, we can use, well, you start from the Boussinesq equation, you linearize and work a little, and you can come up with this equation here, where this is written in terms now of the vertical velocity w here, and the Laplacian is just the horizontal part of the Laplacian here. N here is the buoyancy frequency, and this is the tidal frequency. And from this form of the equation, you can see that there is a characteristic non-dimensional number here, n over omega. And then that is in fact you can also see that the equation itself, it's formally speaking the same as the wave equation. If this were time, this would be the standard wave equation. And so just like the wave equation has characteristics, which is the wave speed, this has a characteristic slope then. And the slope is given by omega over n. And that will be very important in what's coming here. So, but to solve the equation then, we have a fixed frequency. And then to do a simple solution of this, you can linearize the bottom boundary condition. You need a boundary condition from the bottom and also from above. And if we have a small slope of the bottom boundary, you can linearize it. You apply a radiation condition above, and then you can calculate the energy flux, because that's what we need for the ocean circulation. We need to know how much energy is created by these internal tides and goes into the mixing. And then by some standard linear wave theory, if we make this simplified boundary condition, we can come up with an expression for the wave flux here. So in order to calculate the wave flux in a particular point on the bottom, you have to calculate this integral, a convolution integral of the slope, the topographic slope around that point. And that is something, this is just a comment here. So the characteristics of the waves. So these are the characteristic slopes of the waves here. And this, I have here a picture, a kind of bottom topography, which is supercritical. And here the theory and this equation here is not valid. It's only valid for small slope compared to these red lines here. But if you use this assumption, then you can calculate things numerically. And this is a calculation I did some years ago, and where you get the energy flux to the internal wave field from the internal tides over the global ocean. So for instance, 0 here means 1 watt per square meter, minus 3 means 1 milliwatt. This is a logarithmic velocity, logarithmic color scale here. So the main uncertainties, I mean, this global calculation has been useful. It's an important sort of input that you can use for parameterizing mixing in global ocean models. It's also been used now as to parameterize the bottom drag in global tidal models. But there are, of course, still uncertainties and problems with this calculation. And the biggest uncertainty comes from unresolved topography, which I will not talk about now. And the second one is this issue about supercritical slope. And if you calculate, in this particular calculation I did here, actually 50% of the flux below 1,000 meters depth comes from points where the slope is supercritical. So this is really an important issue. And if you look at the theory here, in the linear regime, when you have subcritical slope, then the wave conversion to the wave radiation here increases like topography squared, h squared here. And my hypothesis is that actually once it gets supercritical, then the wave conversion will saturate. And the simple argument for this, I mean, this is really an open question here. The argument for this is that once the height of the topography is so large that you have this supercritical slope, then there is kind of a shadow zone which is not really seen by the wave characteristics anymore. And increasing it's just a hypothesis is then that as you increase topography more, you don't get more topography above this shadowing point, and consequently you will have a saturation. But this is what we want to investigate experimentally now. So, yeah. So now I'm coming to the experiment, which started only a few months ago, earlier this year. So we only have preliminary results to show here yet. But it was done in this large water tank in Toulouse, which is 30 meters long, 3 meters wide, and 1.6 meters deep. And then you can create in this tank a linear salinity stratification with a buoyancy frequency around 1 radians per second. The topography here, we create a topography which I will show shortly. It's placed on a false oscillating bottom plate. And then you can easily vary the period and the amplitude of these oscillations. In this experiment, you also prevent reflection both horizontally and from above. And that is a bit different from almost all other previous experiments, where they have actually a usual rigid surface or a reflecting surface from above. And the diagnostics we use is synthetic scleron and PIV. And so far we have only results for the simpler synthetic scleron. Okay, so this is one kind of topography we have used here. This is sinusoidal topography with 10 ridges in a row like that. And then the diagnostics are taken in a kind of a window which is about 1 meter, a little more than 1 meter wide, like that. And so this is the false bottom plate, and this is attached to a vertical rotating rod like that. And since the attachment point is it's asymmetrically placed, when this rotates, this bottom plate is oscillating back and forth here with the frequency omega. Above here, this is the water surface. Now this is not to scale, this is actually much thicker, this above the green line here. Here we have a wave absorber, which is folded plastic net here. So almost no waves are reflected back down here. And this, as I said, this is not to scale. It's 10 centimeters high here and 1 meter wide. So actually these are the slope is very small in fact. Here is another kind of topography. We've used a number of rounded walls like that. Again, periodic, or we can also make, here it's very flexible. You can actually place these with almost any distance we want here. But yeah, just to compare with some theory, with the first experiment, we've done it periodically here. Okay. And some preliminary results. So these are pictures obtained from the synthetic scleron. And what you get from this is that, well, you send optical rays here, or you take a picture of where you have a kind of a pattern behind the water, and you look through it, and you get a deviation because of the perturbation due to the internal waves. The wave rays are bent, and you can understand then by some theory that what you see, the deviation of the ray, I mean the sort of apparent movement of this pattern behind the experiment is proportional to the deviation of the stratification here. So this is what we see here is pictures of the deviation of the stratification from the background, which is a kind of measure of the amplitude of the wave. And so we have 4 different cases here with the same topography, just varying the forcing period of these oscillations. And yeah, you can't really see the color scale here, but I can't see it myself here either, even on the screen here. Yeah, so the scale goes up to only 0.9 here, and here is 2.5 and 3.7 here. So actually, I mean, it's an adaptive color scale. In fact, the amplitude is much lower on this picture than on the others. That's the main point. And you can also sort of see that here you have a comparatively stronger amplitude in between the ridges than above. And here it's sort of the opposite almost. So actually, in this particular case, you have a much weaker wave radiation. Okay. And to understand that, we can look at the next picture here. It turns out that we have a kind of a resonance or interference phenomena between these ridges here. So in this case here, we have when a wave characteristics sort of generated here at the top of this ridge reflects on the bottom and then hits the next top here. It turns out that this is a constructive interference. The same thing here. If you turn up the frequency more, you can have a wave ray reflecting 3 times like that and again hitting the next one. This is constructive interference. And that corresponds to, as you can see here, so 5 minutes, okay. So this is corresponds to the, I think, the second case I showed before, and yeah, which one? I think this one actually, to the first one here. So this is, here you have a reflection down here and up here, and this constructive interference is so strong here that you actually get a more or less turbulent field here. And then here in this one, you have a destructive interference when a ray comes down here, reflects in the corner and goes back again here. Then this interferes destructively with itself, this wave ray, so actually there's a very weak weak radiation from above. And here you can see this clear. We vary the forcing period here, which means also that the slope is continuously varied in many experiments. And here you can see the case with the destructive interference, constructive. So the three of the pictures are here, here, and here, the three experiments I just showed you. So we also, and this is as another part of this project, which is conducted by Leo Maas, who's here in the audience, and also Alexander Passy again, and Bing Yuan from the Netherlands here. They have particularly studied what kind of topographies that can be conversionless. Again, a kind of a destructive interference, but in this case, in this part of the experiment, he has a solid surface, not a solid surface, but a reflecting free surface here, no absorber above, and a single ridge. And again, you can vary the frequency, and for a certain particular frequency, it turns out that you have a destructive interference and almost no wave radiation, as seen on the next picture here. So this is this special frequency. We have no generation of internal waves. Okay, so this is just some, as I said, some preliminary results. What remains to be done mainly is to do more processing of these data to obtain actually the energy conversion. What I showed, the pictures I showed here, for instance, this one. This is not the energy radiation. This is just a simple measure of the sort of integrated amplitude of the wave above topography. What we really want to do is to get the energy conversion here, energy radiation from these waves, and to see how it scales with various parameters of the experiment. But this we have not done. Yeah, and then finally, a few words about future work here. We also want to check. I mean, this has been simple. I've just shown a few of the experiments which we have actually done. We are also going to do some work with irregular topography, and some of this has been done, although I haven't shown it. And as I said, also we want to calculate the energy flux and investigate some scaling relations. And then if I could perhaps add a very last comment here. No more slides. Yeah, and that is that something that would be extremely interesting to add to this experiment is to see the effect of these internal waves on sediments and resuspension. And I have been collaborating with some other people working on sediment dynamics, and I think the effect of these internal waves on the sediment is not known at all almost. And there are ideas that you could use. If you can understand how the internal waves interact with the sediments, you can actually obtain paleo data on paleo tides. I mean, how the tides were maybe 100,000 years ago, 1 million years ago, by looking at how the sediment cores, the structure of them. So if anyone is interested in here in the audience or about actually doing something with sediments on this kind of dynamics, that would be interesting to discuss. So.
We're running a little bit behind time, but I think we ought to have time for one or maybe two questions. So has anybody got a question they would like to ask?
Thanks. Jonas, just to go back to your first few slides. No, you don't need to show them, but when you're talking about the sandstone problem, you need to have mixing, and that the internal tides are a mechanism for the mixing. You haven't really addressed that in these experiments. Is the idea that these internal tides will break in some sense, and that will produce the mixing? Yeah.
Yeah. Okay. And this breaking is not something we study. We're just studying the generation. The general assumption is that once you've generated them, something like 20% of the energy of these go then to breaking and to to the lifting the cold fluid and so on. So that's.
Any other quick questions that anyone wants to ask? One more. There you go.
I'm interested in the sediment movement, and how about the velocity of this? Yes, velocity.
I mean, we've done computations where we know pretty well the barotropic tidal velocity over the global ocean. It's typically a few centimeters, up to 5 centimeters, right? And now the internal tide in this linear calculation, it can add maybe usually it's pretty small. But in a lot of locations where you have rough topography, it can be another up to maybe 5 centimeters. So it can almost. I mean, from this rubbish I'm working with on this problem, he says that typically it's assumed something like 7 centimeters per second and so on. But I think it could also probably be affected by, if you have internal waves, you also have pressure gradients along the sediment, and that could be important, perhaps. That will be an interesting study. That's all I can say.
Thank you very much. I think I'd like to thank you very much for your presentation. I think we don't have time for any more questions, but that was very interesting, and I'm sure there'll be lots of other results from your project, which will come out soon, we hope. Thank you very much.